This is the fun portion, right? You have to sit through this in order to get to the good technical stuff. Before I started, I wanted to wish everybody Happy Father's Day. I don't know if it's an international holiday or not, or Brian's saying it's a Hallmark holiday, so everybody has to buy cards for it. But today is Father's Day in the United States, so happy Father's Day to everybody. I've got 15 minutes and I've got an unbelievable amount of slides, so I'm going to just cut to the chase, but the slides will be available afterwards so you can look through some of the information. I'm going to talk about two things, none of which have to do directly with InfiniBand, but InfiniBand is implicit in both of them. GPU computing, and then I'm going to talk about storage. These are probably the top two topics right now that are the hottest that we've seen from our customers. So I'm going to talk about GPU computing at Dell in particular. Everybody here probably knows about GPUs, so I'm just kind of setting the stage for what our opinion is, I guess, about GPU computing. Is that we all know that hardware changes rapidly. CPUs, GPUs, network, software in particular, I think people tend to forget about. It changes very rapidly. So you have to evolve and adapt to when these things change. But they also happen at a different rate. Intel has their tick-tock model. AMD has got an approximate model. InfiniBand has a different kind of time scale. So all these things happen at different times. So if you buy a GPU compute solution today, is it going to be worth anything tomorrow when everything changes, or do you need to throw it out and buy something new? Of course, Dell would love for you to do that, but we understand it's a big investment. So our whole approach is to be very, very flexible. So to do that, actually I'll get to that real quick, but just to show you a quick point about what happens on the software side. This is a chart that came from Amereto Hess, an oil and gas company developing an application for GPUs. So the red line, the pink line, shows the CPU performance, and the blue line shows the GPU performance as they modified their code. So over several generations, they got a huge change and improvement. And by the way, as CUDA changes or InfiniBand changes, you're going to get some more changes in this. So the point is, as things change, the performance improvement changes, and you need to be flexible and you have to adapt to that. So what Dell's kind of opinion, I guess you might say, about GPU computing is that you develop your application on something fairly small like a laptop or a workstation, and then once you understand the application, deploy it on a cluster in production. So what we've decided to do at Dell for cluster deployments is that we've separated the CPU and the GPU with a PCIe network. So that way I can upgrade the GPUs whenever I need to, or the CPUs whenever I need to, or as applications change, I can change the ratio between the number of GPUs to CPUs. It also allows me to optimize the power and cooling for the GPUs and the CPUs. So for example, if I had them embedded in a single box, I have to optimize, assuming the worst case, stuff full of GPUs and CPUs. But what happens if I use fewer GPUs? My power and cooling is not as optimal as it was before. By splitting them, I can keep them optimal on both sides, the CPU and the GPU. So what we've done is we've created this 3U box we call the C410X, and it's we just call it a box of slots. All it has is 16 PCIe slots, nominally for GPUs, but you can use whatever you want, InfiniBand cards. We've also had a couple of people ask about FPGAs. But there's 10 slots in the front, 6 in the back, still front to back cooling. All the slots are by 16. And then that's inside the box. Coming out of the box, we have 8 PCIe connectors, iPass connectors, or HICs. Everybody's heard those. So in the worst case, you're going to get 2-to-1 oversubscription, 2 slots to every connector. Best case, you can do 1-to-1. It also has redundant power. We have 4 1400-watt power supplies. And the nice thing is we have a BMC controller. So what this allows you to do with this controller is change the number of GPUs connected to each one of those 8 outputs. You can do that on the fly. So if you wanted 2 GPUs at any point in time, great. If you didn't, you wanted 4, you can script actually go through the BMC, assign 4 to that output, and you have to reboot the host node so it recognizes the devices. But once at that time, then you've got 4 GPUs. Didn't have to change anything. No hardware changes at all. It's all software changes. On the host node side, just to give you, if you don't know Dell that well, the top is our C6100, which is the 4 compute in a 2U Intel nodes. Each node has a by 16 HIC, and it's got redundant power. Just in case, if everybody doesn't know Dell really well, this came from a division of Dell called Data Center Solutions, DCS. And I don't have it in the slides, but if you took DCS out of Dell, it'd be the 4th largest manufacturer in the world of components. Unofficially, I can tell you we've sold over 80,000 of these. So there's some parts of Dell that you may not be aware of. Down below it, we have the C6145, which is a 2U box with 2 4-socket AMD systems. Each board has 4 by 16 slots, and it also has a by 8 that you can use for IB or whatever you want. So that combination of the host node and the GPU node give us our combinations that we can use for whatever application. So for example, on the left-hand side, in the middle, you see the GPU box, and above it and below it are either the 6100 or the 6145. Or the right-hand side, you can flip it. If you like, the left-hand side we call the sandwich, because the CPUs are the bread, and on the reverse side is the reverse sandwich. Although I don't think I want to grab a hold of that. So the big question that everybody asks is, great concept, what happens to my performance? Number one question. Okay. So what we did is we compared the C410X with the 6100 to the Supermicro 1U with the 2 GPUs in it. I always forget the number on it. And we ran NAMD. So this is the number of steps per second. So you see, we actually did pay a small penalty in performance for this case. With the Supermicro's a little bit faster. By the way, this is 2 GPUs per system. So in the case of Supermicro, each GPU has by 16 connectivity, and ours we actually have by 8, because remember we have to have 2 GPUs connecting to the 1 connector to the host node. Okay. But let's look at another example. This is the CUDA SW++, Smith-Waterman algorithm. So we're varying the query length, and we're looking at the performance. Dell is in the yellow, Supermicro is in the red, and you can see some places where we're actually faster. So it all depends on your application. In some cases, like NAMD, for that particular configuration, it wasn't as good. But for this application, we actually shown we're just as good, if not better. I can't explain the better part. I haven't figured that one out. But I can explain just as good. But this is what we like to think of in terms of separating the CPUs and the GPUs. And you'll see the red bar on the right is Supermicro, and you see that light green bar, that's the initial result that I showed. 2 GPUs per host node. Okay, but with Dell now, with our C410X, we could say, what happens if we did 4 GPUs? And that's the gray bar in the middle. We get about 80% of the performance out of those extra 2 GPUs. Didn't cost you anything, meaning you didn't have to go buy an extra node with GPUs in it. In the case of Supermicro, you have to go buy a whole box. And by the way, you can't share the GPUs between the box. They're fixed. Real quick, I want to emphasize one of the impacts on software. So everybody knows that CUDA 4 came out with the GPU Direct that Mellanox developed. We worked with NVIDIA on something called a Heisenberg spin glass model. Not my forte. I don't know that area really well. But they modified the code to make it multi-GPU capable using the CUDA 4. So they compared their initial version, which was MPI based. So the code, the GPU would go to the host, which would then go to the other GPU. And that was all done via MPI calls. And they compared that to the CUDA 4, where the GPUs communicated directly without the host. And let's see what happens in terms of performance. So at the top, you see a 256 cube result, and the bottom is a 512 cube result. Overall, CUDA 4 was about 15 to 30% faster than the MPI base. Okay, so with the Dell concept that we can separate these things, I can go 2, 4, or 8 GPUs in that box assigned to 1 host node, and I can get better performance. Whereas if you were stuck with GPUs in a box, you're limited. You can't, it's more difficult to share. You could do it via MPI, but you're going to pay a price in terms of performance. Oh, one other quick comment. This is not always commonly known. It's out there. But if you have a node with multiple IOH chips, the problem with CUDA 4 is they cannot, if you have GPUs attached to each IOH, they cannot communicate via CUDA 4, at least on the Intel side. We're still testing the AMD side. We're not sure yet. So that is a limitation, that you're stuck with multiple IOHs. The second big problem that we've seen is around data management and storage. This is probably the biggest request we get from our customers. And you guys have probably all seen these kinds of comments that storage is about 15 to 25% of the cost of the system, but it's like 90% or 99% of the headaches. But in our opinion, HPC storage is not about just hardware. Don't throw hardware at it. It's a solution. You need to look at it from every aspect: the hardware, the software, the client, documentation, best practices. That's what we've seen with some of our customers that use Lustre. The reason they get frustrated with Lustre is not because of Lustre itself, it's because they configured it incorrectly. If they would have done it correctly, they would have had no problems. But at the same time, we can't find 1, 2, or 3 file systems or solutions that somebody says, those are the leading solutions in storage. And you can see the IDC study, 25 customers were using 13 different file systems. So just like applications, storage is driven by the application, just like compute that's driven by the application, storage is done the same way. So what we've done is we looked at the different aspects of storage that people wanted. These are the 3 aspects that everybody came back to us: performance, reliability, and capacity. Cost is always there. We're not going to ignore cost, but those are the top 3 attributes. So then we sat down, we talked to a number of consultants, and we said, let's develop a box that addresses all of this, and the answer is you can't do it. So then we decided at that point is to address each one individually, trying to develop a solution for each, and then combine them so it's seamless. So that's the strategy that we've been working on, all about flexibility and adaptability for the software. So at the bottom you see the 3 types of software that are storage that we've been looking at, or developing solutions for, I should say. Fast Scratch, which is all about performance. We call primary storage, which is where home directories or your applications are, and that's all about reliability. And then what we call long-term storage, which is all about cheap and deep. Lots of storage, very inexpensive, but we really don't care that much about performance. So we have 3 solutions that we're approaching on the storage side, but we take 2 different tactics approaching each of those solutions. The first is a complete solution. So from Dell, you can say, I want a complete Lustre solution or a complete primary NFS storage solution. Or we also have what we call roll it your own. So you can download the white papers that tell you all the details about how to take Dell hardware and build Lustre on it, or take Dell hardware and build an NFS box out of it if you like. If you want to do it yourself, you're more than welcome. But if you want to roll it, or a complete solution from Dell, we can offer that as well. On the Fast Scratch side, real quick, because I'm running out of time, I've worked with the University of Cambridge, so they have developed several roll-it-your-own cookbooks on how to take Dell hardware and make Lustre work really well on it. But at the same time, we've partnered with a company named Terrascala in the US to take their software stack and their GUI management tool on top of Dell hardware for Lustre. We're also in the UK working with a smaller company named Alsys to develop very similar solutions for the EMEA market. So this is what it looks like. Everybody knows what Lustre is: metadata, object servers, and so on. I'm going to skip all that. On the primary side, at least in the US, we're partnering with Red Hat to bring XFS as a underlying file system for NFS. So again, we've got a white paper that says take the Dell hardware, here's how you can install XFS, and it works really well. Or if you want to buy it as a complete solution, we can do the same thing. Again, also in the European markets, we're partnering with Alsys in the UK to develop the same thing. So this just gives you a quick example of our NFS solution. Right now, we're limited to 100 terabytes, and I can explain that very easily. It's a support problem from Red Hat. They don't have any more hardware than 100 terabytes in-house. so they can meet their SLA. So we're working to solve that problem with them. But the nice thing is over InfiniBand, with this kind of base, just simple NFS storage, we can get 1.5 gigs a second on writes and up to 2.4 gigabytes a second on reads. Really good performance out of just basic, simple NFS. One of the things we did do, though, is you're saying, the question is, what does Dell bring to the table around NFS? It's just NFS. I can build this. You know, we got high school kids who can do this. But what we've done is there's all kinds of options and knobs that you can turn. I can change the I/O scheduler. I can change all kinds of different parameters to change performance. So our engineers sat down and went through an exhaustive study of a number of these to improve performance. So this just shows you an example that they were able to get about 30% more performance by some tuning options rather than just throwing XFS on some hardware and letting it fly. And by the way, these tuning options are available in the white papers. So if you can buy it from Dell, we can show you how exactly we did it and we set it up. Or you can buy the white paper and do it yourself. We don't mind either way. So since Brian told me I have 1 minute left, I'm just going through the different configurations. We've got an HA version of this as well. Particularly, we're probably going to come out with some larger versions above 96 terabytes. So real quick, last slide. The two most requested topics from our customers are all about GPU computing and all about storage. On the GPU computing side, everything's around flexibility, making sure that we can adapt to evolving hardware and, more importantly, evolving software. On the data management side, it's probably the biggest problem that we see from our customers. We need better storage solutions, we need faster, we need cheaper, we need more, we need it now, all those kinds of questions. So we've chosen to focus on 3 different types of storage: fast scratch, reliable, and long-term. I didn't get much of a chance to talk about those. So we're developing a product for each and integrating them together with a software solution. But at the same time, you can buy it complete from Dell, or you can roll it your own, and you can download the white papers and figure out all the magic options that we used and build it yourself. It's up to you. But the last point I want to make is the tools for data management, and we can sit and talk for days about what data management is. Those are becoming very critical. How do I manage my data? How can I understand my data? How can I tell if my data is corrupt? That's one of the biggest problems right now, is how do I tell if the data is bad or not? So with that, I'm going to stop. Thank you.